Hello, this is the group of Kayvon Ghaffari, Jason Moore, and Tran, here to present our CSE 91 project, Automatic Detection Buoys. My name is Jason Moore, and I'll first present to you the problem we are addressing. There are many threats to ocean life in today's world, like pollution and global climate change. To know which species are most in danger, we would like to get data about their populations, but this is a difficult task. Our goal is to specify an automatic system that can recognize and count sharks, which could eventually be extended to other species. I'll now pass it over to Oi to talk about previous work in this area.
Past work with surveillance buoys can be seen with NOAA. Their buoys in Hawaii are currently being used to monitor carbon dioxide and oxygen levels in the ocean and atmosphere. With this, they can understand the exchange of carbon dioxide between the ocean and the atmosphere. Buoys like these are also being used to monitor water quality issues. Cali T2 has developed the idea of buoys for surveillance of the world's coral reefs. With the equipment that it would carry, it would be able to travel the ocean on its own, collecting data. For the specifications of our buoy, we will construct it with cameras securely mounted. It must be able to function for long periods of time without maintenance, so as not to disrupt the natural populations there, as well as be able to take colored pictures so that one can identify and differentiate between the different classifications of sharks. The framework will come from pre-existing buoys that have also performed analysis of water pollution and also transmit that data to a database. We will be making it out of steel, considering that it is one of the most durable metals in the world and also abundant and lightweight. And because of the equipment it is carrying, we estimate the size to be 4 by 4 feet with a height of 5 feet. Finally, for the power source, we will attach solar panels and a group of batteries to power it.
The relationship between the speed of transferring the data images and quality of the images is give and take. Since we would be taking color images of the surrounding areas, the file size of the images would be even larger. Once again, color images would be necessary to classify the different ocean species correctly. The problem that arises is the amount of pre-processing that the buoy itself would perform on the images it captures before transmitting the data to the main database on land. A possible solution would be for the buoy to transmit the entire image with its wireless transmission device. Although this would reduce the computational needs of the buoy, it would undoubtedly increase the size of the file to be transmitted. On the other hand, the buoy could perform all of the classification and counting on board and only transmit the important data. This would allow for a dramatically reduced file size, but would in turn dramatically increase the computational needs for the buoy. Increasing the computational capabilities of a single buoy would prove to be costly and complex. The buoy is meant to take the place of a human so that it does not disturb the sea life in the area that it is capturing data. The increased computational needs would require the buoy to be constructed with more devices, thus making it larger. There is, in fact, technology available that both enables high transmission speed and high transmission quality as well. Although this technology is expensive, it would be far more efficient and economical for the buoy to be responsible for only the capturing and transmission of the data images.
The images we take will be large files, and we'd like to compress them to make transmission and classification easier. The method we propose using is PCA, Principal Components Analysis. A full explanation will take too long, so here's a simple example. The left figure shows some data in standard coordinates. Note that each point requires 2 numbers to represent. However, if we rotate the coordinate axes to be aligned with the vector 1, 1, then we can represent each point with just 1 number, effectively having the necessary space to store a point. We can later re-expand the data to its original form. If we think of the images as points in very high-dimensional space, where each pixel is 1 dimension, we can see the potential benefits of re-representing them this way, and the transformation is not too computationally intensive. To perform the actual classification, we will use the LogitBoost method, which is similar to the AdaBoost method, training the system on mini images of sharks. The method basically trains many small classifiers to identify small features of the image, like an eye, a fin, etc. We then take the best features and treat them as inputs to a higher level classifier. This method has been shown to work extremely well for face recognition, and we hope it will work for shark recognition as well.